All right. Hello, everyone, and welcome to our MICD seminar today. So today we have the honor and pleasure to host Professor Michael Herbst from the École Polytechnique Fédérale de Lausanne. Professor Herbst received his doctoral degree from the University of Heidelberg in Germany and was followed by postdoctoral appointments at the École de Pont in Paris and in Aachen, Germany. And since 2023, he's been an assistant professor with a joint appointment in material science and engineering and in mathematics at EPFL. Professor Herbst is a member of several international collaborative projects. In particular, I'd like to note the Marvel Center on Computational Design and Discovery of Novel Materials at EPFL, who I had the pleasure of visiting during my sabbatical and who hosted me in Switzerland. I had the pleasure to interact with Professor Herbst during my visit, but as well as the Center for Exascale Simulation of Material Interfaces in Extreme Environments at MIT, and the Extreme Scale Mathematically Based Computational Chemistry project in France. Professor Herbst is the developer of the DFTK software package, the DFT Toolkit, which is written in the modern Julia language and is designed with an emphasis on simplicity and adaptability, so you can develop, you can take it, adopt it, and adapt it to your specific situations. And so the main theme of his research is to understand the errors in simulations in materials modeling and how they affect our predictions. So we have a pleasure today to hear him discuss with us the topic of algorithmic differentiation in plane wave DFT. So let's welcome Professor Herbst and for his seminar.
Yeah. Thank you very much, Manos, for the great introduction. Thank you for having me here, for the invitation. It's my first time here. I really enjoyed all the discussions I've had the pleasure to have up to this point. There's a few more things scheduled I'm also looking forward to, but now you are first hearing from me about some of the recent work that we did in my group, exactly on, if you want, exploiting the fact that our density-functional toolkit, this plane wave density functional theory code, is flexible and in particular tries to target multiple different, if you want, user communities. We're trying to make the code useful for mathematicians, for people who actually work on physical models, for people who do high-performance computing, and to an extent also, to take ideas from these various communities and import them across the directions. And one of these ideas is this idea of, if you want, algorithmic differentiation, so the idea that you can actually compute gradients of a particular code using some algorithmic tools instead of manual labor. And in particular, we have been working on this framework and come up with a way to, if you want, look at different input parameters from classical DFT computations, so things like parameters of this exchange correlation approximation, part of the modeling, things like strains, external geometries, other modeling parameters, and really try to compute derivatives of output quantities, forces, band structures, with respect to each of these input quantities in a systematic way, right? And ideas that we can use or exploit this with would be, for example, to really use a gradient-driven approach to designing new materials or new functional approximations, right? So, for example, how to really tune the band gap here of gallium arsenide in a particular way. And I will talk about a few examples how to do that later in the talk. First, of course, let me thank the people who really did the work. So here, mostly, this is the work by Niklas Schmitz, my first PhD student, and Bruno, my second PhD student, whom I had on this for the past few years. My group is still growing, and I should also say that actually in the background, I may not have too much time to talk about this, but a lot of this work has actually been fueled by improvements also on the algorithmic side for response function and gradient computations in DFT, and there's a bunch of people from the mathematical community that I've been working with over the years to make this happen. Now, for those of you who are not so much in materials modeling, let me first kind of give a bit of a broad motivation, why even focus on this density functional theory. I think from my point of view, we have a lot of problems in the world that require new materials. Materials fundamentally limit what kind of physical properties we have available to choose from to come up with innovative ideas for, new batteries, for example, new ways of solving energy or distribution problems. And basically, to fuel this nowadays, starting from a simulation-based procedure is quite common. And so here what I show is the usage of one supercomputer in Europe, in the UK, Archer 2, and all the blue stuff is basically electronic structure simulations, and the deep blue stuff is basically density functional theory. And you see that over the past years, there has been a very solid 33 to 50% occupation by just these kind of simulations, right? So this is really something that happens in the millions as we speak. And therefore, looking at this from the mathematical point of view, from the point of view of making developments easier, I think is a worthwhile effort to help us solve these problems. Now, kind of flipping to the other side to give you a bit of the flavor of the type of mathematical equations that we have to get into. DFT is, from what I would call from the mathematical point of view, a non-linear eigenvalue problem, right? In the end, these guys here, these orbitals are the unknowns, and to get them, we diagonalize this operator here, and in particular, in this operator, there's a potential that depends on this green density expression, which in itself also comes again from these orbitals. So that's the nonlinearity aspect of this eigenvalue problem. And for the structure of this talk, it's mostly relevant to keep in mind that this somehow has two steps, right? From some density, some guess of this green density, we can compute a potential. That would be essentially evaluating this V function here. Having this potential, we can build this operator and diagonalize it, giving us a new density. That's this F function here. And of course, if basically the density that we put in is the density that we get out, then we have solved this nonlinear problem. Okay? So this is kind of the structure that we have to deal with as part of this talk. Now, getting basically one step deeper at modeling materials, the question you usually ask yourself is, you have a structure, maybe motivated from some naturally occurring material, you run your simulation, and then you ask, does it actually give me something useful? Now, what does this mean, something useful? Well, of course, we're talking about properties, right? That's what we care about in material science. And then the question, of course, comes up, well, how do we get properties? Right? I told you so far something about orbitals. Maybe you saw the energy that was popping up there. But this is not a property. Right? The point is that properties is what tells us from a theoretical point of view, how does my system respond to external changes? Right? So for example, if in an experiment I change the electric field and I see how my material changes, that's a property. Right? So this is really the connection. Properties are really giving us the connection between theory and experiment. And therefore, kind of what we actually care about is not so much solving this expression, but getting one step further and asking the question, how does this self-consistent density here actually depend on parameters in my setup, right? Because these parameters theta are exactly these external conditions. Fields we apply, structures, strain, that's what I mean by properties. But of course, there's other kinds of thetas, other kinds of parameters that are lurking in here. For example, the model that we use, if you want the precise functional form of this potential V, right? That also depends usually on some parameters in my setup. Like, for example, something I determine from physical relationships or by fitting. So this is also, if you want, one parameter. Other things could be like talking about materials design. If I vary the strain of my system, I can tune properties, very important for semiconductors, for example. So actually, if I'm able to actually compute derivatives of my DFT simulation with respect to these external conditions, that leads exactly to this inverse materials design I was alluding to. Other thetas are, for example, the numerics. Right? In the end, if I solve my problem and I'm able to understand how does my answer depend on the numerical parameters that I've chosen, then this gives me some understanding of the error that I make in DFT. Right? So what I'm trying to convince you here is that actually being able to compute properties or derivatives of DFT codes, that's not just something for sort of like connecting to experiments, but there's really a whole bunch more when it comes to the design of new models, physical models, when it comes to the understanding of numerical errors that really goes in here and is at play. Now, the whole point of giving you this motivation is to say, well, one particular advance that comes from the computer science direction actually allows us to really do computation of these gradients through an entire code. That's essentially the idea of algorithmic differentiation, namely exactly the ability to compute derivatives of arbitrary output quantities with respect to arbitrary input quantities, which I showed on my first slide. Now, we are, of course, not the first people and the only people to think about this. So there's actually a bunch of efforts that have appeared in the past. They have been working on this. I should say that there's this whole divide in the typical simulations between the types of basis sets that you're using. Most of these efforts so far have been coming from the setting of isolated systems using Gaussian basis sets. What we are doing is we're using plane wave basis sets, and the mathematics behind this is very different. And as a result, the ideas that have been proposed over there could not be just simply used. Like, there have been some additional numerical and algorithmic developments that we needed to do, as I mentioned, basically done in collaboration with my mathematical colleagues. In particular, another point I want to point out that these codes have usually been forked, meaning that they are really off-branchings of development, and it's not necessarily kind of going on in synchronization with the main development efforts. On the other hand, what we have really been trying to get to in the Density-Functional Toolkit is we've tried to make it possible to really simultaneously develop algorithmic differentiation techniques with the rest of the code. So our code is in particular not a fork. And what we basically have done in terms of algorithmic differentiation should, in principle, compose with the other components, such as GPU acceleration. We haven't gotten to this point, but I don't think it's too difficult. And another point I want to point out is that really this differentiability, this algorithmic differentiation effort, that's something that came later. The main motivation for the code was to work on mathematical questions in density functional theory, and having, in some sense, the right structure, we just realized that something like this could be done with rather reasonable effort. Now let's go a little bit more into the details, how to actually compute such derivatives. I already mentioned before, this is this SCF problem that defines most of DFT. Now, if I just ask the question, what happens if I modify a little bit the potential that I insert here? And if you want, I'm just propagating this change in potential linearly through my code, right? And then what I do is I get, if you want the Taylor expansion, I get a derivative of this function f. I get a derivative of this function v. And basically, by just a simple rearrangement, I get this expression here. So if you want, if I'm changing the potential and I solve this equation, then I get the change in density, okay? Which means that I'm able to actually compute the derivative of this implicit function, the density defined in terms of all the parameters of my simulation. I'm able to compute this derivative by solving this problem here. And that's what people typically call density functional perturbation theory in this community. Other names are Dyson equation for this particular equation, and there's a few other names as well. The key point is that we have this so-called independent particle susceptibility, the derivative of this potential to density map. And here we need to invert this operator here, which is usually also called the dielectric adjoint, right? So this is the dielectric operator, the adjoint of it. Okay, so this is the problem we have to solve. And if we are able to do that in a generic way for arbitrary right-hand sides, arbitrary derivatives of this potential, then we're able to compute arbitrary derivatives. Now, let's go into a few ideas and a few things what this could enable. So I mentioned that if we're able to really look at the change of an output quantity with respect to, for example, an input parameter, then this parameter could be a model parameter, and this could allow us to refine models. So what we're doing here, for example, is I'm looking at the optimal lattice constant predicted by density functional theory, and I'm comparing this to experiment, and I'm basically using this as a guiding to improve on the exchange correlation functionals I will have a slide with more detail later on. Another idea is, of course, as I said, a parameter could be the strain that I apply to a particular lattice. And then I can ask the question, what strain should I apply in order to get exactly a kind of band gap that I'm interested in? So these derivatives, the band gap versus strain, or for example, the derivative of the relaxed geometry with respect to the DFT functional, this is exactly the sort of stuff we are interested here. Let me mention that, for example, in this case, we actually have multiple processes we have to differentiate through, right? Because this is not just a single density functional theory simulation for one setup of the parameters, much rather we actually here we're optimizing also the lattice, right? So we have an inner loop, which is this the density functional theory computation, and an outer loop, which is really the modification, the optimization of the lattice parameter to get the minimal energy structure, so to speak, right? So our code and our framework is able to handle this, if you want, this complication that they are able to really go through multiple levels of simulation. Now, what does this look like on the level of, again, if you want, computation? I mean, I already mentioned this SCF problem, and if from a density, for example, we're able to compute a quantity of interest, and we're now interested in the question, how does the quantity of interest change with respect to some parameter, for example, some strain, then we just apply the chain rule. And in particular, in this chain rule, this derivative of the density with respect to this external parameter pops up again, meaning that if we're able to solve this problem, we're able to put it in here, and we're able to compute the derivative of these quantities, these output quantities, with respect to an input parameter. So to give you this example, for the case of the exchange correlation optimization, what we did here is we used a fairly small standard data set. We trained on just 4 structures to keep things simple. These are the structures shown here in gray. And what we did is exactly to optimize the optimal lattice constant that comes out of our DFT simulation for a given set of parameters, meaning that we had a comparison, a loss function, very simple again, just a square loss to compare against the experiment. And here we have this inner minimization problem that I mentioned, where we both optimize over the DFT density as well as over the lattice constant. Now, the challenges here are that, of course, this is multiple nested iterative methods that we have to get through. And in fact, actually, in order to compute the derivative of the optimal lattice constant with respect to this quantity, with respect to this, these external parameters theta, these density functional theory parameters, we need to solve this Newton step, which means in particular we need this derivative of the energy with respect to the DFT parameters and the external lattice constant. That's a very unusual derivative, so something that in practice you wouldn't have. So my point here is that if you want to be able to do these kind of developments, you will be faced with new kinds of derivatives that you need to compute, which in practice you don't necessarily all want to implement yourself. Band gap tuning is just another example. So here actually I'm even going one step further, and I show you the real code. So this is what it looks like if you code it up, and this is what happens if you actually then execute it. So and what I want to point out is that what this is doing is it gives, like, it has a function where you are given a strain, so an external strain you apply to the crystal. For this strain, it builds a model, it discretizes it, it runs the SCF, it computes the eigenvalues, and then it goes through the eigenvalues exactly to find out what is the band gap, right? So this is kind of what you would code up to do a DFT computation and find this band gap. And now in order to do this optimization, you just need to add a few lines of code. You define your loss function, and then you call an optimization library with a loss function. You say that you want to use a second order method, and you say, please use forward diff whenever you need to. Right? And this is all that needs to be done. So in the background, this will notice that in order to use a quasi-Newton optimizer, it needs a gradient. And so then it will automatically compute the gradient of this expression. And basically in the background, it will run the required density functional perturbation theory expressions and compute the required gradient and just compose it with the derivative that is needed for the quasi-Newton optimization. Right? So this is really the full code to produce this example. And my point is that this is really easy, like in the sense that somebody who doesn't know DFT, who doesn't know how to compute derivatives, would be able to just code this up and get going with this. And this is what we're trying to get to really make things simpler and make it easier also to use the code. Now let me talk about one other story. That's the question of uncertainties and uncertainty propagation. The idea behind this is to say, well, I mean, if we have a way to quantify the uncertainty in, for example, DFT functional parameters, model parameters, there are some models out there which allow us to do that. Could we use that and push it all the way through our computation to an output quantity of interest? Right? So basically knowing a distribution of my DFT functional parameters, how do I get a distribution of my quantities of interest? And there the answer is essentially fairly simple. If we know, for example, that our parameters are Gaussian distributed, or we assume that, then we can just push through, that's an linear approximation, this uncertainty, and basically by knowing again this Jacobian, so this gradient of the quantity of interest with respect to theta, we are able to actually push through this uncertainty all the way through our DFT computation. And again, if we know how to do density functional perturbation theory, this is actually not a big problem. And indeed, we're able to do this, like again, on the example of an optimal lattice constant computation. So basically what I'm showing here is I'm using this beef set of functionals. So that's a DFT functional which has exactly this kind of Gaussian distribution for the parameters built in. So here we basically, again, propagated through both the computation of the optimal lattice constant and the DFT computation, and we're able to really produce now, based on these density functional theory parameters, a distribution of possible optimal lattice constants. Let me just highlight that in blue here is our output, which basically requires one single computation and one gradient computation. In orange, this would be an ensemble approach, where basically for a drawing of parameters, you would do the full computation, so 10 full geometry optimizations, which of course is really, really costly, but just to give you an idea for the benchmark. In practice, people are also using ensemble methods where they reuse densities that are computed only once for a mean set of parameter, and then just basically do an equation of state fit. So this is, if you want, a bit circumventing the problem, but just to give you an idea that the results are overall similar. And therefore, this kind of linearized push forward by just using a like end-to-end differentiable DFT simulation is something that you can use to really get from DFT functional parameters that are associated with a distribution to quantity distributions, if you want, independent of the quantity of interest. Another point I want to mention is basis set error. So I mentioned that the theta could also be basis set parameter. So for example, the cutoff parameter of your plane wave discretization. And there, in fact, very recently, collaborators of mine have come up with a way to estimate the basis set error in the density of a DFT computation. And what we are now able to do, exactly because we have this forward propagation of the error, we're able to take the density error and push it to quantities of interest, like, for example, of the forces. And here, both of these plots show the reference error that is, of course, computed at a very high cutoff, and the density, like the estimated error that we get by our linearized error propagation scheme. And I think the key point, again, to highlight here is that having something like algorithmic differentiation, which allows you to compute this arbitrary input to output relationship, these arbitrary output to input derivatives, if you have, in some sense, this working once, like you have it working for the density, from there you can access the error estimate in pretty much arbitrary quantities. There's some caveats here. If you're interested, I'm very happy to talk about them more in the questions. But in principle, at least, things are working like that. Now, what I haven't told you so much is actually how to make this work. So how do we really get this arbitrary possibility of computing derivatives with output versus input parameters? So basically, how do we really avoid this combinatorial explosion? And this is exactly where the idea of this algorithmic differentiation comes in, because there, what you do is you basically look at, if you want, the computational graph of your problem, and then you really go in this forward mode algorithmic differentiation box by box, and you duplicate the graph with the appropriate derivative computation. So usually when you do a DFT computation, you prepare somehow your model, so you prepare the potential right? So this means like you compute it from the given parameters, then you solve your self-consistent field, right? Then based on this self-consistent field density, you compute maybe some follow-up quantity of interest, and then you have the full quantity of interest based on your parameters. Here it's exactly the same thing. We need to prepare this derivative. That again we can do by really looking into the precise computational routine that it used to build the potential and step-by-step differentiate it. Once we have this, we just send it to the density functional perturbation theory solver. It essentially goes through and solves this problem, giving us this density response. This we send further to the result of applying the chain rule to the actual computation of the quantity of interest, again, basically by taking this AD technique one level deeper. And then we get the derivative of the output quantity of interest with respect to the input parameter. So in some sense, if you're able to do this for generic right-hand sides in a numerically stable way, and you're implementing this once and for all, as we have done in our code, whatever theta and A is doesn't really matter so much. And this is exactly how we have done it. Particularly, the AD framework in itself takes care of really composing all these boxes together, right? So as soon as you're able to tell this framework, whenever you encounter an SCF computation in the computational graph, please use the appropriate response computation to compute the derivative, then you're done, right? Because the composition of all the individual boxes, that's exactly what some AD framework is doing for you. And that's pretty much what we have done. Essentially, we took our response solver and we exposed it as an interface to an algorithmic differentiation library called forward diff in Julia that does this composition for us. Now, one thing I want to highlight here, being also halfway a mathematician, the nice thing about this is that now this box, namely this computation of the response, is completely decoupled from all the rest, right? So people who actually don't know so much about the physics can work on this isolated problem. And people, however, who really want to work on new gradients, they don't necessarily need to know so much how this problem is solved, right? And so this is kind of the idea that if you are able to encapsulate the problems locally, people can work on the problem separately. And I think this goes by this catchphrase, which I took from Alan Edelman from MIT, people compose where software composes, right? So I'm very much convinced that in interdisciplinary research, it's very important that people can work on their own separate problems, but somehow manage to get this into a joint software framework to basically benefit from each other's advances. Now, just let me give you one word about accuracy in case you wonder. So here we have actually coded up elasticity, elastic constant computations, where both the stress as a derivative of the energy with respect to the applied strain, as well as the elastic constant, meaning the derivative of the stress, again, second derivative, if you want, derivative of the stress with respect to the strain, that is both computed using algorithmic differentiation. So this is basically AD through SCF, right? This is what we're basically doing here. I should really highlight that the implementation pretty much looks exactly like these formulas. So it's very simple, like finite differences. However, because it's based on response theory, it's more accurate than finite differences, right? So the blue curve here is the accuracy we are able to achieve for various parameters of the SCF tolerance, where you see that actually you need to really tune very well what parameters of finite difference step size you use versus your SCF tolerance to get a nice result. Of course, in practice, often you don't need to go to 10 to the minus 10 in the elastic constants predictions. That's arguably true. But it's just to show you that at least with something like AD, you don't need to worry so much about these parameters. Okay. So I have a little bit of time, so I just wanted to show you how this actually works in practice. So I have a small notebook here where I just basically wanted to walk you through if you want, the computation again of this optimized band gap with respect to an applied strain. And so if you want, the fundamental question here, of course, is how does our band gap change as we apply some external strain, right? And so this is exactly where the idea comes from, to write a function that computes the band gap given, for example, here the lattice constant. So as I said, you just basically code this up. And then if you ask for the computation of the derivative at a particular, here, a particular lattice constant, in the end, in the background, it will really run these, these response theory computations and give you this derivative. And so if you then want to really do the full optimization, in the end, you're able to do that by simply asking the library to do the computation of the derivative in the background, right? So again, the idea is that it's really easy and simple to play around with this, to look at the derivatives, and as you're going along, you're basically able to compute and optimize parameters such as here the lattice constant appropriate to give you a certain band gap. Something else I wanted to quickly highlight, this idea of using derivatives as a way to design new materials is, I mean, if you want, it's just, again, a derivative of a quantity with respect to some parameter. That's not the only derivative where this can be applied. Another idea is to look into exchange correlation functionals. So here, again, I'm doing probably the most possible simple thing you can do. Namely, it's a Slater X alpha model where you just scale a little bit up and down the Slater exchange. So the idea is that this basically the scaling of the exchange is just one parameter. You can code up in a few lines your custom exchange correlation functional that has this parameter. Then you can insert this into the standard construction of a DFT model in our code. And you're able to ask the question, well, what happens, for example, if I now change this value, and what happens if I now, for example, compute the derivative of some output quantity with respect to this value? Another point that is actually fairly simple with a flexible code such as ours is to look at algorithms. So just to give you an idea, if I want to solve, for example, SCF problems, there's a whole plethora of possible algorithms I could look at. And here I'm looking at the most simple one, the so-called simple mixing algorithm. The idea is that we, inside the DFT, Density-Functional Toolkit, this function f that I was putting on the whiteboard or on the slide a few minutes ago, that is actually exposed to you as a user as a function. You can just use it and play around with it. So for example, here, this would be actually the kind of algorithm you want to implement, and this would be the corresponding code to implement this algorithm, basically a one-to-one translation exactly using the infrastructure that the code provides. Again, it's fairly easy to slide that into a computation. So for example, here we do a standard silicon computation and just supply a new solver, and then you run it and you get the result. And what I haven't shown you so far is that actually inside this algorithm, there's a small parameter called damping. And this I coupled here to this slider. And now what you see is that because of the interactivity of this notebook, I can actually play around with this parameter, and interactively the code will rerun, and it will basically show me immediately what's going on. So for teaching scenarios, or when I want to play a little bit with parameters of my computation or my algorithm, this is something which is very easy and very practical. And another thing I didn't tell you is that this works on the GPU, right? So in the end, if I have exactly this code, and I just ask for this to run on the GPU, and I have a GPU, which my laptop doesn't, then this works, including the interactivity, right? So I can basically interactively play with GPU kernels as I'm basically going along. This will, of course, not be high performance. I should really say this, because, of course, interactivity like this has a performance penalty, but it's something one can do, and you basically don't, you don't have to work very hard, right? So this is actually something that works on the GPU. That's GPU code, right? So that's something which is basically enabled by this flexibility of the Julia language, and is something that in the development of new algorithms, it's very, very convenient. Okay, I have 25 minutes, very good. So let me just give you a few more points on this AD business. So if you think this is all great, let me just give you a few words of warning. So life is unfortunately not always easy. So I mean, I mentioned that in principle, this DFPT problem becomes very central, so you need now a good solver. That's something we worked on, but there's definitely still room for improvement. Another point is that sometimes, you know, the thing that you want from a physical point of view may not necessarily be the gradient that you're asking for. So what I'm trying to say is just because you're able to compute every gradient of an output quantity versus an input quantity doesn't mean that this gradient makes physical sense. Right? So you still need to think. And in particular, if you do your setup wrong, then you get wrong answers. So here what we're doing is we're using an algorithmic differentiation to compute a certain derivative of the density with respect to a perturbation that breaks lattice symmetries. So of course, if you don't take this properly into account, you get the wrong answer. Only if you take it into account, you get the right thing. Right? So you still need to think a little about how you set up your derivatives and how you do your computation. The other problem is that not everything in first principle simulations is immediately differentiable. So band gap, for example, if you have some bands that join, that's not differentiable. So there you need to think a little bit how to do that, how to regularize it, and how to basically circumvent these problems. Basically, physical observables, though, are usually kind of summations over different bands or things like that. And then usually the summation is differentiable, even though the individual thing is not. So you basically need to make sure how to propagate the derivatives in a way that you're not losing out on, on sort of these mathematical relationships that the sum would hold. I know this is very abstract. I can go into some more details in the questions if you want. But overall, kind of hiding some of these details, keeping convenient interfaces, that is really, to me, the challenge of all of this. And this is something we try to address, but where certainly still some work that needs to be done. Now, let me just peek at these algorithmic developments that we have done in the past. So actually, since the SCF problem in itself is nested, right? You have the outer SCF and you have the inner diagonalization that you have to do for every update of the density, of the potential. This means that also the derivative becomes a nested problem, which here manifests in the way that every time you apply this independent particle susceptibility, you have to solve what is called the Sternheimer equations. And the problem there is, of course, that, or not of course, but the problem there is that for metallic systems, it turns out that actually solving these Sternheimer equations can become quite hard, right? It can actually need hundreds of iterations for a particular k-point to actually compute the to solve the respective Sternheimer. So that's one of the things where we worked on, because as it turns out, if you use some of the information that you have during the SCF, some of what people call partially diagonalized bands, then you basically are able to exploit the fact that on the Sternheimer computation, you have a block, this first block with these partially diagonalized bands, where the Hamiltonian is actually diagonal, right? So if you're looking at this structure and you're using it inside this solver, then you're able to actually target or you're able to actually cure some of these badly behaving points, and overall you're reducing the number of iterations that you need to take to converge the Sternheimer equations. A similar thing that we did is we looked at tolerances, right? Whenever you have nested solvers, it's a bit tricky to choose the tolerances of the inner solver. That's something where I worked with a master's student to actually come up with a mathematical theorem that tells us exactly how we should use the inner tolerance with respect to the outer tolerance. And that's something that overall allowed us to reduce quite a bit on the number of, again, iterations that need to be used at the inner Sternheimer equation level. So this is what I'm talking about when I mean algorithmic improvements that are necessary when you're getting to the final, to problems that you want to solve for arbitrary right-hand sides. Finally, DFTK, just to mention, we have 10,000 lines of code. So it's fairly easy and simple to look at. Nevertheless, it's been now useful for, it's been like things like GPU support. We added recently AMD and CUDA, and something like 1,000 electrons is easy to do. And people from different communities have in the past been contributing. I just wanted to mention this. So we have recently started to do a bit more systematic performance comparison. So in particular for systems which are large, so things like here, this is an aluminum slab. In these cases, we actually are now comparing to quantum espresso in a way that we are actually faster than them on certain situations. This is not true for all systems, though, but overall, on larger systems, we seem to outperform the code a little, right? So this is mainly to convince you that the performance is okay, right? I'm not saying we're high performance everywhere, but the point is using this is not necessarily like using a slow code. We have some algorithms that we used in the past to optimize performance of SCF. That's something we used to do. We recently started to look at integrating the code a bit further into this AIDA framework that has been developed on the side of Marvel. And also we are looking at using ideas from the mathematical theory of DFT. Here, for example, Concham inversion, something we recently looked into to kind of just give you an idea of the bandwidth of the code where it's able to not just solve individual problems, but really try to add to both the application side as well as the mathematical research that's going on in the field. If you're curious about errors and error control, there's a workshop coming up in Lausanne. We're still accepting people who are interested to apply. So that's at the end of November. And I'm leaving up here the summary, I think, very briefly. And yes, that's more or less the last slide. If you have any questions, I'm more than happy to answer them right now. Thank you very much.
Thank you very much, Michael. So, the talk is on for your questions. Yeah. That's not me.
Yeah, thank you, Michael. It's great talk. Maybe, so you said that the density is normally differentiable.
Yeah.
But could I not have things like bifurcations and things like that, so whilst I may be formally differentiable, I can in principle have bifurcations and things of this nature, so I have a cusp at some point. So there's small points where it cannot be differentiable. I see this in classical modeling when we're trying to do things like implicit derivatives a lot.
Yeah.
That's a good point, yeah.
Taking, for instance, degeneracies. You could have like a degenerate state, and then you apply differentiating with respect to any parameter. Right? If that breaks a degeneracy, then you can actually, maybe the derivative is not even well defined at those points.
No, that's a good point. I agree. Yeah, I haven't thought about that. But just to kind of add a little bit to what I was actually referring to, I mean, my point is that if you look at what's sort of behind this, it's the idea that while individual eigenvectors of your operator may be non-differentiable, if you actually take the sum of them, then you get something which is differentiable, right? So that's a little bit the point. But here you're right in the sense that, of course, the density kind of selects exactly, if, for example, in an insulating case, an exact discrete number of states. And then, of course, yes, you can have these situations. I agree. But from the point of view of the AD framework, this is a curable problem, right? You can always regularize and try to, you're removing effectively, we're doing what we are doing when we're modeling metals, right? You remove a step function and make it a sort of a smeared out function that is differentiable, or what the people do in the community of neural networks, right, where they don't use a max but a soft max, or these sort of tricks, right? So I agree that there may be cases where it doesn't work so easily, but I'm pretty sure that even though there's non-differentiabilities, there's some tricks you can play to push this a little bit further than just all quantities of interest that are strictly speaking differentiable. Yeah.
Fascinating talk. So when you're computing the response derivatives of an observable Q with respect to theta, you also have the partial derivative Q with respect to theta, right? So,
yes.
I mean, all of your talk was focused on figuring out the
yes.
derivative
yes.
rho with respect to theta. Can you comment a little bit on the other one?
Yes. Yeah. I mean, so this is exactly what, if you want, the beauty of AD is, right? The fact that if all of the individual building blocks, if there's a rule that tell you how to take the derivative, then the AD framework can compose this using the chain rule. And so here, what I really mean by building block is how to multiply two matrices, right? So it really goes to a very low level. And in principle, actually, for the self-consistent field algorithm, we could do that same thing, right? It's just that we have chosen to not do that, because then we would really have to go through each of the SCF iterations and each of the diagonalization iterations of each of the steps, which, of course, compared to just solving the response theory problem, is much more costly, right? So in some sense, the idea here is similar to much of this Julia framework. The idea is that you first get things to work using a very generic way of solving it, like here, for example, how you really differentiate all the steps through all the steps, including matrix multiplication. And then you realize, oh, there are some places where you can tweak performance, and then there you invest the effort on coming up with a good algorithm. That's why I've been focusing so much on the DFPT, because in the end, that turns out to be the computational bottleneck. So if you're saving 20% by coming up with a better algorithm, that really results in 20% in the overall computation. Whereas the rest is kind of taken care of automatically by the framework. Yeah, so that's why I didn't talk about that. It just happens.
Thank you, Michael, for a very interesting talk. So I had a question. So apart from the fact that a quantity being not differentiable, there is also the issue that, for example, I'm thinking of a simple case where you have the band gap versus strain. Even if it can be differentiable, it is not necessarily physical to do that thing, which is like if I'm thinking of a biaxial strain, if I do it that way, it will not taking into account the fact that my third direction is relaxing.
Yes.
So I was just curious, does this also fall into the regime where you would say, hey, you need just to smartly pick which quantity you do? For example, in this case, maybe it's the Poisson ratio that you should do rather than the band gap itself if I want a biaxial strain. Yeah. I'm just curious how you kind of balance, or how someone who does not necessarily know the algorithm that well balance kind of these things.
No, I agree with you very much. I mean, in the sense that, first of all, thank you. I was waiting for that question. But you're absolutely right. So I think there's, if you want, a domain-specific way of solving the problem. And that would be how you mention it. Okay, there's actually sort of a better variable to describe the system. Right. And that variable is basically giving you the right way to take the derivative. The other solution is that you actually are naive and you just add another layer. For example, here you would say, I have a part of the geometry which is fixed externally, and then I have a part where I do another layer of optimization, right? I haven't done this here, but in principle, I could do that, right? I could just have, sort of my function is given sort of a bifurcating strain or something, then I optimize the free parameter, and only then I do my DFT computation, right? And as I've shown in the case of the optimal lattice constant, that is doable, right? You have your entire workflow, you code it up, and then you push the derivative through, right? Of course, in that particular case, it would definitely not be as efficient. Because if you do that, there's additional steps and additional loops, and additional loops means that there's additional gradients that have to be computed. Another thing, just because it fits this topic, let me point out that if you look at these unusual derivatives that I was mentioning right here, that if you are the order in which you take the derivatives matter, right? Because if I take the energy and I differentiate with respect to something like theta, the first derivative, there I can use Hellman-Feynman. But the second derivative, where I differentiate that gradient with respect to A, there I actually have to solve the response theory problem. Which means that if I have here 100,000 parameters, and maybe here only one, it's a good idea to do Hellman-Feynman here. Which means you wouldn't actually take the stress and then differentiate with respect to the DFT functional parameters, but you would do it the other way around. You use Hellman-Feynman to compute the energy with respect to DFT parameters, and then you use the response theory to differentiate with respect to the stress. Right? So of course, these sort of things, yeah, there you need to know the details. Right. But you will at least get an answer, which is the correct answer, even if you don't know the details.
Okay, thank you.
All right. Thanks, everyone.
And you have a quick question.
Thank you, very nice talk. I have a question. So is the choice of optimizer important here? Like in the demo, you choose the BFGS, like standard optimizer, but there are like other optimizers like built in the code, and even in the practical DFT calculation, the choice of the optimizer will maybe affect the final results. Mm-hmm. So do you have a benchmark for that? Thank you.
So first of all, this actually I didn't stress this, but this library that we were using to optimizing the lattice constant was not built into the code. Actually, this is a standard Julia library that we just used, and basically behind the scenes, the library was calling the derivative computation in our code. So that's, if you want, actually partly the point of using Julia, that you don't have to do this all in your code. You can actually compose from what is out there. Does BFGS matter or not? Like, of course, if I use an algorithm that doesn't require derivative, like for example, this was a very simple 1D problem, I could have just used a derivative-free optimization algorithm. Then, of course, you know, there will be no computation of the derivative. I have to say we didn't benchmark this because that was sort of not the point. But here it just took 2 BFGS steps to converge, which I think is, well, pretty good, right? So I'm not sure if other algorithms are also able to do that. For the SCF case, yeah, sure, it matters what optimizer you use. I mean, this is actually, if you want, that's part of other research that we did that I briefly mentioned when it comes to SCF algorithms, that actually being able to have algorithms which automatically adapt to the type of problem that you have at hand is quite advantageous, right? And so that's indeed something where people have invested a lot of effort in the past to come up with better optimizers, and I don't think the final word has been spoken there.
Unfortunately, we have to leave the room for the next class that's coming in. So let's use our time to thank Professor Herbst again very much.
Thank you. Thank you very much.